Hello students, today we are going to see about entropy, source coding theorem and Huffman coding. In this video, I'll be explaining about the need for data compression, basic idea of compression, information and entropy, source coding theorem and finally Huffman coding. Huffman coding is one of the type of source coding algorithm. This Huffman coding will be explained in detail with an example here. So what is compression? Compression is nothing but you're going to reduce the amount of data which is used to represent a source. Here the goal of compression is to represent a signal or a data in its more efficient form. Compression is mainly needed for increasing the transmission speed and decreasing the storage space. Consider if there are raw data. Consider a text data which requires about 6 MB storage space for storing a document with 1 million word. In case of audio signals, it for just 30 seconds of audio signal it requires about 5.3 MB of storage space, and in case of image it requires about 5.5 MB. It is more than 1000 page text document. In case of video, which is the largest source of all data, it requires about 7.86 MB for just a black and white video, which uses 30 frames per second, and 23.6 MB per second storage space for color videos. So as you can see, the raw data occupy more storage space, and it also needs more time for transmission. To overcome these drawbacks of data, we are going for compression. But some say that the capacities of storage medium and the communication data rates are increasing rapidly. But we can see that the quality of data on the other hand is also increasing at the same pace, so compression is naturally needed. And wireless communication is also increasing, which is again the reason why we have to go for compression, because in case of wireless communication the amount of data which has to be transmitted and the quality will be high, whereas the given space for transmission bandwidth range spectrum will be limited. So this ensures that the need for compression. So what is the basic idea of compression? As I already said, it is nothing but you're going to reduce the amount of data which is required to represent a source. The basic idea here is you're going to exploit the redundancy in the data. Redundancy is nothing but the repeated information in the data which can be coded efficiently in order to reduce the size of data. So this is all about compression. You're going to reduce the data which is used for representing the source. This compression can be divided into two broad categories, which is lossless compression and lossy compression. In case of lossless compression, only the redundancies in the data will be used for compression. Once the compression is done, you will be exactly able to reproduce the original data. That is the use of lossless compression. There won't be any loss of information there. In case of lossy compression, the original data not only has redundant bits, but also there will be some data which can be sacrificed, which nearly contributes to the which has less contribution to the original data. Those kind of data can be discarded actually, but in this case the original data cannot be recovered back. That is, the original data cannot be reproduced exactly. There will be some degradation in the reproduced data. This is all about lossy compression. So you have to compromise between the quality and the amount of data in both in lossless and lossy compression. So compression in analog to digital communication, as we have seen before, which includes sampling and quantization. When you convert an analog signal into digital signal, it requires sampling and quantization. Both these techniques are a part of compression. Sampling, it is a lossless compression unless it follows the Nyquist rate. That is, the sampling rate should, when it is higher than the Nyquist rate, then it is a lossless compression type. When it is less than the Nyquist rate, then it's a lossy compression type. When you sample the signal below the Nyquist rate, then there will be some loss of data, which implies that it is a lossy compression technique. And quantization, we all know that it is a type of lossy compression, because you're going to quantize the data for a particular range of value. We're going to assume only a single value. that is digitizing the value. So there will be some loss of data. So quantization process is a lossy compression process. So as I already said, there will be some trade-off between the quality and the amount of data. If you want to get a good quality data as output, then you have to have good amount of data, that is the storage space will be high. If you can sacrifice some quality, then the storage space can be reduced. So entropy comes into picture here, which is one of the most important term which is used in information sharing, because entropy will give you the minimum number of bits that can be used for coding a symbol in the data, coding the symbols in the data, which is the minimum number of bits required. Below that, if you go, you cannot reproduce the data exactly. It is the minimum number of bits required to exactly reproduce the data. So when you always have different symbols in the data, that symbols, it can occur many times in the data, so you have to calculate the probability of occurrence of each and every symbol. Say the symbol ranges from S1 to Sm with their probabilities P1 to Pm respectively. Then the entropy of the source is given by H, which is denoted by summation I is equal to 1 to m pi log base 2 1 by pi, where this pi is the probability of occurrence of the symbol Si. When you use this formula and calculate the entropy H, it gives you the minimum number of bits that can be used for coding the data without any loss of information. This entropy is actually needed to compare whether the coding algorithm is good or bad. Say if you are using an algorithm, and if you calculate the average length of bits, length of code words that you have come out with coding the source, when you calculate the average length, if it is equal to the entropy value, then you can say that your algorithm is an efficient algorithm, and there is no other algorithm which can code more efficiently than your algorithm. If you say that the average length of your code is slightly higher than the entropy value, then there will always be a efficient algorithm which can code better than your algorithm. So that is where entropy can be used to compare the quality of the technique which you are using for compression. So with the help of this entropy, source encoding theorem has two characteristics. One is, as I said before, if your algorithm produces the code word which is whose length is exactly equal to the entropy, then your algorithm is a uniquely decodable efficient algorithm. But when the average length is higher than the entropy value, then it means that there is some other encoding algorithm available which can code your data more efficiently than your algorithm. So these are the two theorems. When it is equal to the entropy, then it means that your algorithm is the best. If the entropy value is slightly lower than your average length of the code word, then it means that there is some efficiently codable algorithm available. So this Huffman coding is one of the source encoding algorithm. It is a lossless compression technique, and it is also uses variable length codes. Variable length codes means for each and every symbol you have to find a code word. That code word will be of variable length here in Huffman coding. For frequently occurring symbol, you will be having less bits in the code word, and for rarely occurring symbol, you will be having more number of bits in the code word. That is a variable length code, and it is uniquely decodable. As I said, there won't be any loss of data, so you can decode the original data exactly. And it is also prefix free. It means that no code is prefix of another code word. And this Huffman coding is used in many applications like JPEG, MPEG, and it's also used in fax machines. Now let's see about the Huffman coding algorithm. This screenshot gives the procedure of the encoding using Huffman. Initially, we have to calculate the probability of occurrence of each and every symbol, and that probability has to be aligned in decreasing order, that is in the descending order. You have to align the probability in descending order. then these two probabilities will be added to get the new probability, and again it will be aligned in the descending order. Then this process continues by adding the least two probabilities and finding the new probability, then aligning them in the descending order until you reach the last two probabilities. When the last two probabilities are reached, then you have to assign the bits uh, like 1 and 0 for the different probabilities. Then you have to traverse back from where you got the probabilities. You have to traverse back by giving the same code word as the first bit, and again introducing 1 or 0 for those split numbers, so that you will get, for the next process you will be having two code words. So last two probabilities will be given 1 bit code word, and then when you traverse back and you go for the previous column, you'll be getting two code 2 bit code words. Then this process continues until you reach the first column. So this Huffman coding algorithm is very simple and very effective, and it can be easily understood with the help of a simple example which will be shown here. As I said, the symbols and the probabilities has to be calculated, and the probabilities has to be assigned in the decreasing order. So the symbol A, B, C, D, E, F has a probability ranges which is aligned in the decreasing order, and the least two probabilities are added. 0.06 and 0.04 are initially added to get 0.1, which is again aligned in the descending order of probability. Then again the least two probabilities 0.1 and 0.1 are added to get 0.2. Then again the least two probabilities 0.2 and 0.1 are added to get 0.3. The same process continues, and the least probability 0.3 and 0.3 are added to get 0.6. So once the final is reached, that is the final step is when there are only two probabilities, then you have to stop with that and start assigning the bit values. That is shown in the second table. When you traverse back from 0.6, 0.4, first assign the binary values as 1 and 0. Then this 0.6 is not the original probability. It is obtained by adding the least two probabilities in the previous column, which is 0.3 and 0.3. So you're going to traverse back by giving the initial bit of the code word as the actual code word for 0.6, which is 1. So 0.3 and 0.3 gets the first bit code word as 1. Then you're going to differentiate them by giving the next bit as 1 and 0. So for 0.3 it is 1 1, for the next 0.3 is 1 0, and 0.4 is the original probability which will be aligned 0 for all the columns. Again this last 0.3 is not the original probability, but the probability which is obtained by adding 0.2 and 0.1. So the code word of 0.3 will be carried back to 0.2 and 0.1 as the first two bit. So to differentiate these two code words, you give again a third bit as 1 and 0. So you get 101 for 0.2 and 100 for 0.1. And again the another 0.3 which has 11 as code word, which is the actual probability, so it can be carried backward for the other columns also. Then here in 0.2 and 0.1, this 0.2 which is circled is not the original probability, but the probability obtained by adding the least two probabilities of the previous column, which is 0.1 and 0.1. And these two probabilities will have the first three bits as the 0.2 code word, which is 101 101, and then to differentiate them you add another bit to the code word as 1 and 0, so that they will have unique code word. And this 0.1, which is the lowest one, which is not the original probability, but it is obtained from the least two probabilities of the previous column, which is 0.06 and 0.04. So you carry forward the code word for the first 4 bit as 1010 for 0.06 and 0.04. To differentiate the code word, you again add a 1 bit to the prefix as 1 and 0. So for each and every probability, or for each and every symbol, you get a unique code word. So this is the method by which you can generate code word using Huffman codes. So now finally I have obtained the code result, which for A the code word to be used is 0, for B it is 1 1, for C it is 1 0 0, for D it is 1 0 1 1, and for E it is 1 0 1 0 1, and for F it is 1 0 1 0 0. As you can see, the code result shows variable length code words. It means that the higher probability symbol gets the lower length least length code word, which is 1 bit code word. So since it is occurring frequently, we are using least length code word for that symbol. And f, which is used only in the probability of 0.04, which is the least occurring symbol, it is given 5-bit code word. So this is how variable length code word works, and these are the code words which can be used for symbols using Huffman codes. Now let's calculate the average length for these code words which we have obtained using Huffman code. This average length of code word, since it is a variable length, by seeing we cannot find the average length of the code word. But if it is a fixed length code word, by seeing itself we can say what is the length of average length of each code word. But here we have to calculate the total length, then by calculating that we can calculate the average length. So average length formula directly we can use here, which is nothing but the summation of product of code word length with a probability. That is, for symbol A, the code word length is 1 and the probability is 0.4. So 1 into 0.4 plus, next for symbol B, the code word length is 2 and the probability is 0.3. So 2 into 0.3, 1 into 0.4 plus 2 into 0.3. Next for C, 3 into 0.1, and for D, 4 into 0.1, and for E, 5 into 0.06, and for F, 5 into 0.04. So all these numbers are added to get the average length as 2.2 bits per symbol. So using Huffman code, you can efficiently code the symbols using 2.2 bits per symbol. Now it's time to check whether this Huffman coding worked efficiently or not. So for that you need to calculate the entropy value. Entropy formula already have shown you, which is h, which is given by summation I is equal to 1 to m pi log base to 1 by pi. Here pi is nothing but the probability value. This probability value you can take it from the table for each and every symbol: 0.4, 0.3, 0.1, 0.1, 0.06 and 0.06. So you have to apply these values in that equation, and we know that log base 2 can be converted into log base 10 using this equation. Log base 2 of x can be written as log x by log 2, which is base 10. So when you convert it and calculate the value of h, you get it as 2.14. Now the entropy value is calculated to be 2.14, but the average code word length which we have obtained using Huffman coding is 2.2. So this code word length is slightly higher than the entropy value. This is not always the case, because sometimes Huffman code gives the best possible result, which will be same as entropy value. But for the given example, for the given data source, Huffman coding can efficiently code with 2.2 bits per symbol only. It is slightly higher. So we can say that the average length of the Huffman code will always be greater than or equal to the entropy value and less than h plus 1. When you see some other example, sometimes this entropy encoding algorithm will be the efficient one. In that case, the h value and the average average code word length obtained after encoding using Huffman algorithm will be same. But in our case, it is slightly higher. So it means that there is some other coding algorithm which can code efficiently than Huffman coding for the given data. So this is all about entropy, source coding and Huffman coding. Hope you all understood. Thank you.